Hi, we're back to discuss integration techniques, and in this video we will focus on the last of our integration techniques, which is called partial fraction decomposition. Now we would use partial fraction decomposition if the integral is not basic, if previous methods, substitution, integration by parts, or even algebraic methods fail, and you would integrate by partial fractions if you're dealing with a proper rational function whose denominator has two or more factors. Recall that a proper rational function consists of a polynomial at the numerator whose degree is smaller than a polynomial at the denominator. Here's an example of such a case where we have a rational function with the numerator factored into two linear expressions. Other cases may be observed, such as the second example, where a repeated linear factor is observed at the denominator, along with a linear factor. There's also a third type of factor, which could appear. In this case, we have two linear expressions that are joined by a quadratic expression. We have frequently created common denominators to regroup multiple fractions. In this example, common denominators can be created and then the numerators can be joined. This is an operation we've gotten accustomed to. Partial fractions is the exact reverse operation. It is obviously much more difficult. For instance, although I can tell you the rational function on the left can turn into the combination of 1 over x, 4 over x squared minus 5 over x plus 1, the question remains, how do we do this? So the rules of partial fraction decompositions go as follows. If n of x and d of x represent polynomials that generate this rational function, then if L of x is a linear factor contained in the denominator, the decomposed version of n over d will contain a constant over that linear factor. If R of x is a repeated linear factor of order k, in other words, if you see R of x to the power k, then the decomposed version of n over d must also account for this factor being repeated by including it in k different terms, where the denominator R of x has powers 1 to k. Finally, if q of x is an irreducible quadratic factor of the denominator, then it too will be part of the decomposed form n of x over d of x will turn into, and its numerator will have a composition of cx plus d. The constants a, b1, b2, bk, c, d will have to be determined by us. These are just arbitrary names for the time being. For instance, in this first example, 2x plus 1 is written over two linear factors, x minus 5, x plus 2, neither of which are repeated. The decomposition suggests that we can find a constant over x minus 5 and a constant over x plus 2 that will equate the two sides of this expression. In our second example, x minus 1 is cubed at the denominator, and therefore three different terms will be required in the decomposed format, x minus 1 to the 1, to the 2, and to the 3 in three separate fractions. Their corresponding numerators could be different and will have to be solved for eventually. The last factor is x plus 1 is linear and non-repeated. Finally, in our last example, we have two linear factors that are non-repeated and therefore do not require we take into account repetition in the decomposed form, and we have a quadratic term, x squared plus 1, which requires we need to incorporate a cx plus d expression at its numerator when decomposing it. So let's follow the guidelines in the following example to describe how a proper rational function can be decomposed. We're going to use minus 4x squared plus 5x plus 4 over x squared times x plus 1 as a guiding example. So first and foremost, we're going to write the general form the rational function will decompose into. Observe how x squared is actually a linear factor that appears twice. Hence, a over x and b over x squared being its decomposed form. X plus 1 is a linear factor without repetition, and it justifies our third term being c over x plus 1. Now we need to figure out what values a, b, and c must take for this equation to be true. In step 2, we will rewrite both sides so that they share the same denominator. Using the left-hand function's denominator as a guide is the best thing to do. Notice a over x shares 1x with the left-hand side's denominator, but is missing a second x and an x plus 1. b over x squared shares the x squared that the left-hand side has, but doesn't have the x plus 1. c is already divided by x plus 1, but doesn't have the x squared term. We will simply incorporate the missing elements from each fraction so that the denominators left and right become all the same. And once the denominator is common to all terms, we can regroup their numerators. Now, if two fractions have the same denominator, guaranteeing their equality means we simply have to compare their numerators, and that will be step 3. Compare the numerators. The numerators can be made equal, or the constants for a, b, and c can be found by using nice x values. When I say nice x values, we're looking for values that can help us focus on solving one of the unknowns rather than all of them at the same time. For instance, if x were to be replaced by 0, the left side of our equation will become 4, and the right side will have the a and the c terms disappear, leaving b times 1. And therefore b has to equal 4. If we choose x to be minus 1, the advantage is the x plus 1 terms on the right will both go to 0, leaving only the c term. On the left, using minus 1 will give us a value of minus 5, and therefore minus 5 equals c will give us our third constant, or the third constant in our decomposed form. We've run out of good values, so at this point we could just choose any x value and implement it into the equation we started off with. So the left-hand side would become 5. The right-hand side, by replacing x equals 1, would become 2 times a plus 2 times b plus c. But now remember that b and c values we've already found, and therefore we could solve for a. With the a, b, and c values that we've now just found, we have obtained our decomposed form for the rational function. Here's an alternative to the step number 3, which involved using nice x values. What we could do is expand the right-hand side, so distribute the terms, and then regroup the terms that have similar powers. So here we've moved around ax squared and cx squared that are like terms and regrouped them as a plus c x squares. X's appear in two different spots, ax plus bx, and we can join them. B is the lone constant. And then we can compare corresponding powers left and right. Constants. On the left, constants are equal to 4, and on the right, b is the only constant term. So b must be 4. Multiples of x. 5 is the multiple of x on the left. A plus b is the multiple of x on the right. And because b is already known to be 4, a has to be 1. Multiples of x squared on the left are minus 4. On the right, a plus c. So a plus c must equal minus 4. Because a is already known and equal to 1, then c must be minus 5. And once again, we have found values for a, b, and c that will make the decomposed form equal to the original proper rational function. With the new coefficients, we're now ready to replace our integral by a composition of simpler integrals that may involve power rules, substitutions, logarithms. So we're back to previous strategy.